Hello, Sauce here. This is a video lesson on introducing area under the curve. Area under the curve is a quintessential project in calculus. And the pre-calculus course introduces the concept. This is a short review. Area under the curve can be abbreviated AUC. And what we mean by curve is really the area under a function or between a function and the x-axis. We traditionally call it curve, but it's a function, and that function doesn't even need to be curved. It could be the area under a function, which is a line. Let's give a visual example of what we're talking about. I'm going to graph a piecewise function. I'm making it up, and these pieces are linear pieces, or we have two linear pieces, and we might call this a constant function. 3 pieces, piecewise function. What do we mean by the area under the curve of this? We mean the area between the function and the x-axis. And we might need a starting place in the domain. Typically we could give it the letter A, and an ending point. We don't need an interval to ask what is the area under the curve, but we can, and we often do, ask what is the area under the curve on the interval, in this example from A to B. And our curve is a piecewise function with 3 pieces. Let's give another visual example. Here I'm going to make up a function that does do some curving, and I'm going to establish an interval on the horizontal axis from A to B. The area under this curve is going to be more sophisticated because the function actually curves. I can highlight with shading what I mean by the area under the curve, which again is the area between the function and the x-axis. And notice in this second example that we go below the x-axis, which creates a region that is under the x-axis and would be counted as a negative amount. I'm going to give names to these 2 functions. Piecewise function we're going to call G, and this curving function we're going to call F. How would we calculate the area under the curve of these? Well, we have strategies. We have a few different ways in which we can do this. And the strategy is going to match the situation. One strategy is to think about using geometry. Formulas that we have for the areas of rectangles and squares and triangles are reliable when the area under the curve, in this case represented by a shaded region, is one of those reliable geometric figures. For example, the area under G is 3 regions, the first of which is a triangle. We have another triangular region, and this region here is a rectangle. So if we knew the measures of these lines, we can put them into the formulas for areas and rectangles and add up those areas to get the area under G from A to B. I could use symbols to give notation to that question. Capital A in front of parentheses stands for area, and we would say we're taking, or we want to find the area under the G function from A to B as a double inequality. Again, this is notation for the question, or what stands for the area under the G function. We have a comma, and then we must express the interval on which we want to take the area under. We could ask the question in a different way. We could simply use language and say, area under F on, and then interval notation. Two ways to express the same question or the same idea with different functions in this case. The geometric strategy will not work for finding the area under F. Because F is a curved function, we don't have reliable formulas for finding the area of a region such as that, because it's a pretty sophisticated region. The shape is sophisticated. It's got curving sides. So we have a way of finding a crude estimate, and that is simply to count squares that belong approximately to the regions that we've shaded. For instance, this region here is going to include at least one whole box and most of a couple others, and then a little corner of a fourth. So a very crude way of estimating if the box was 1 unit on a side would be approximately 3 units, because I'm counting 1, and then this little piece can make up for these 2, which are nearly full. Very crude, but that is a way that we can establish an estimate. This region here would have 2 full boxes, and it looks like half approximately of 2 more. So I'm going to say that's about 3. And the region here is going to be 1, 2, 3, and I'm going to combine these into 4 and a little bit more, so I might say 4.5. So very crude estimate, 4.5 for the area, 3 and 3 here. But this region being under the x-axis is going to be considered negative. This region is the sum of negative values, so the area is going to be a negative region. If I'm going to find the area under F on A to B, I add then these 3 regions together, and I would get approximately, well, these would cancel out, leaving approximately 4.5 as a crude estimate. Geometrically, I can find this exact. This is a 1 by 3 triangle, so the area inside of it is half of the rectangle, which is 3, or 1.5. This triangular region here is 2 by 2 triangle. The square would be 4, so half of that is exactly 2. And the rectangle is a 5 by 2 rectangle, making an area of 10. These are all positive regions because they're above the x-axis. We had to add them together to get 13.5. And that's an exact estimate because we used reliable geometry. There is another way of estimating, and it is more accurate. It can be very accurate, and that is the technique that we introduced in pre-calculus of dividing the rectangle or the region that is expressed shaded here as rectangles. If I use this strategy of function values being the heights of rectangles, then I can break up each region into rectangles, which I can find the exact area of. And if I add up all of the rectangles, I can approximate the total area under the curve. But the rectangle method is still going to be an estimate because every time we make a rectangle, we're going to have a little bit that is over or under the actual function curve. And so the amounts that the rectangles are over and under is called an error. And it is certain to be, the sum of the rectangles is certain to be a little bit off of the exact area. But the more rectangles we use, the more accurate our estimate will be. And this area model using rectangles is a process that can get to a better estimate than simply counting boxes in the shaded region. The way to calculate the exact area under the curve requires calculus. And the way that calculus gets the exact area is to use the rectangle method, but also the concept of infinity, so that we can perform the mathematics on calculating an infinite number of rectangles, which means that the error of each rectangle becomes infinitely small, and therefore the sum of the infinite number of rectangles becomes the exact area under the curve. That's the concept, but the math behind that process, something that we'll be learning in the next few months.